Yeah, so next up are the continuous grid-based approaches, which are also following online-offline frameworks. I just realized that we are a little bit running out of time for this week, so this is the final podcast for this week, and we will continue with the change detection next week. So anyway, those grid-based approaches are, as you may think, based on a grid-based model. So a grid structure is used to capture the density of the data set, and a cluster is just defined as a set of connected dense cells. So the batch clustering model, or the batch clustering approach, which is most similar to this one, is for example Sting. The appealing feature again here is no assumption on the number of clusters. We can discover clusters of arbitrary shape, and we can handle outliers, which we already discussed are appealing, especially for streams. Yeah, in case of streams, the grid cells are considered as summaries, microclusters. So we obtain or aggregate summary information for cells, and we update these summaries on the grid structure as the stream proceeds. And one of the sample methods, or the sample method I want to show you here, is DStream. So DStream uses a fixed grid, so it divides each dimension into L partitions. So for d-dimensional data sets, we have L to the power of d cells, which is a lot typically if d is a little bit higher. So DStream proposes only to maintain populated grid cells, because otherwise it's much too large, and those are maintained in a hash list. Yeah, and for a populated grid cell C, the following summaries are stored or aggregated. So T update is the last update time for this cluster feature, so the last time where a point has been added. T spore is the last time where C has been removed, or a point has been removed from C. And C is the like in DStream, in DenseStream, sorry. The number of points weighted by the time frame, or weighted by time, so accounting using damped window aging. Then we also store a label, which is the cluster label, and we store a status of the cell, which is either sporadic or normal. We will see what that means on the next slides. And the overview here is that, as I said before, it follows an online-offline paradigm, meaning that we have an online mapping of the new data objects arriving through the stream onto the grid cells, where it fits in, and maintaining the grid cell information summaries we just talked about from the previous slide. And then we have an offline computation of grid density and the merging of dense grid cells to form bigger clusters. Yeah, and there are, similar to the DB-scan variant here, DenseStream, we have 3 cell types which are defined by 2 parameters, 2 thresholds actually, a threshold for dense things and a threshold for sparse things. Sorry, there is an underscore missing in LaTeX, but anyway. So a cell is dense if the number of points in the cell is greater than the dense threshold. It is sparse, so an outlier if it's smaller than the sparse threshold, and if it's in between, it's in transition from sparse to dense, or vice versa. So it's transitional, it's marked transitional. Yeah? And connected regions of dense or transitional cells form a cluster. So sparse is basically the lower threshold. So as long as a cell has more than tau sparse points in it, it is considered to be dense enough to form or to be part of a cluster. Yeah, and changes to the status field. So we have this status field here, the status summary. Changes to the status field occurs in the online component, and the status is set to normal if C changed from sparse to any other type. So from a sparse cell to dense or to transitional. Yeah? First of all, it would be probably transitional. And the status is set to sporadic if for C the number of insertions into this cell is less than expected since the last update, which can be computed by the assumption of an equal distribution of points over time and over data space, of course. Yeah, so in the online phase, the grid cells are maintained. So if a new observation, which is called xi here in this list here, so I'm sorry for that, it should be read here xi. So for a new observation xi, we determine the grid cell xi falls into, that's easy. And then we add C to the hash list if it has not already been in there. Otherwise, we just do nothing here, of course. Then we update the summaries of the cluster feature summary of the grid cell and set the status to normal if the type changed from sparse. Yeah. And additionally, after t timestamps, which is timesteps, which is again a parameter, we delete all grid cells from the hash list that have been marked as sporadic and did not receive new points within the last t timestamps. Yeah, so those that are sporadic and did not receive any new points within this period of t timesteps are just deleted, and we mark sparse grid cells as sporadic if some requirements from the previous slides are met. The sporadic thing here are met, and then we adjust the clustering. And in the offline phase, as I said before, you can use the summary information to compute bigger clusters from neighboring dense or transitional grid cells here. Yeah, short discussion. So it's again a single scan stream compressing thing using microclusters. Model inherent is a noise and outlier handling. We have an aging model again for entire cells now, not on the point spaces, but for entire cells, for entire microclusters again in that case. We have constant parameters over time. So what about clusters with changing density, of course? So all the thresholds L, all the parameters L and this thresholds T dense and T sparse are fixed over the whole stream. So again, we have the problem like all of those methods actually. And of course, the number of grid cells that may be populated, so that should be stored in the hash list, increases with increasing number of dimensions we have. So this is so just look up all the discussions we had for the curse of dimensionality. We may expect that we have, well, at least we have L to the power of D cells, and in the worst case, we have, if we have say n points seen so far from the streams, from the stream, sorry, all the endpoints are just in one single cell. So we have potentially n cells in the hash map, and that is increasing with increasing time, with increasing processes of the stream. But of course, we have this aging thing where we delete grid cells after some timestamps. So T somehow eases up this curse of dimensionality effect here, of course. Yeah, that's it for today and for this week. As I told you before, we'll stop here. We'll continue next week with the change detection methods and then also with the classification and data streams. I hope you are still motivated and still on track. And I'm also hoping that you are healthy, and we'll see you, or I'll talk to you next week about change detection and classification and streams. See you there.